Hello, very good afternoon, sir.
Good afternoon. Am I audible?
Yes, sir, you are.
Yes. I think now we may start, right?
Yes, sir, for sure. We can start. So before starting, I'd like to welcome you all the participants for this session 2 on transfer learning of CNNs. And I'd like to thank our respected Rakesh Sanodiya, sir, for taking this session for us. Thank you.
Thank you very much, Isita. Is my screen visible now?
Yes, sir, it is visible.
Very good afternoon, dear participants. So as in the morning session, you studied about the different architectures of convolution neural network model, right? And means yesterday we started the topic convolution neural network model. In the first session, the speaker talked about the theory of convolution neural network model. Then in the practical session, like the speaker implemented how basically you can implement the convolution neural network model, right? In the today's morning session, so like Ramakrishna sir talked about different architectures of the CNN model. So in this module, basically, we are going to talk about the transfer learning. So what is transfer learning and why the transfer learning and when you are going to use the transfer learning. So after this, after introduction of this transfer learning, so you will see that how like existing pre-trained models, like different architectures of CNN, as you have seen in the morning session, like how you can implement those architectures for different tasks. Okay. Okay, so further, I would like to acknowledge to the course like Mike X Cohen Master Deep Learning course. So most of the contents, again, I have taken from this Udemy course, and also I have taken help of the AI tools such as ChatGPT, Grok, and some like the knowledge which I have gone from these lectures available online. Okay, so the first topic is transfer learning. And what is transfer learning? Why the transfer learning, and when you use the transfer learning? Okay, so in this topic, basically, you are going to see the definition of the transfer learning. So what is the meaning of transfer learning? Why transfer learning is so useful in deep learning, and when to use the transfer learning, and how to use the transfer learning. Okay, so transfer learning. So transfer learning, as name itself indicates, so you are transferring some knowledge from one particular domain to another domain. Okay, so before explaining this transfer learning concept, so I would like to take a very simple example, right? So let's say you means I hope all are the programmer, right? So somehow you have started learning the programming like from your BTech onwards, or like 10th or 11th high school or high secondary school onwards, right? So usually, let's say if we talk about the Java programming language or C++ programming languages, okay, so let's say if the person knows the C++ language, right? And if he try to learn the Java language, okay, so if the person knows or student knows the C++ language, and if he start learning the Java language, then it will be very easy for the student to learn the Java language, right? So he may not be spent so much time on learning the Java language. So let us talk about the scenario. If student doesn't know about the C++ language, and directly he start learning the Java language. So in this case, what will happen? So student has to give more and more time, right, to learn the Java language, right? But what happened, right? So when you already know about the C and C++ language, and if you are learning the Java language, so why basically it is taking the less time, right? So of course, like intuitively, like your mind, or like you are also transferring the knowledge, right, from C++ language to the Java language, right? So intuitively, so like because these things you have, when you are going to learn any new task, so intuitively you have been doing, your mind has been transferring the knowledge from one particular task to another task, right? But coming to the machine, right? So let's say if there are two machines are there, if one machine language C++ language, and another machine knows the Java language, right? So if another machine is going to learn the Java language, right? So here what you have to do, so you have to transfer the knowledge, right? So if you are transferring the knowledge from one machine to another machine, then you call it as basically the transfer learning. Okay, so let me take a one more very real life example, right? If you know how to ride the bicycle, right? So of course, like definitely you might have spent more time on learning the bicycle, right? And if you start learning the bike, or car, right? So it will take a less time, right? But if you directly start learning the bike or scooty something, right? So it will take the more time, right? Why this is happening? Basically because there are some common concept, right? So which are common in both riding the bike or riding the cycle or bicycle, right? So how to make the balance, right? So all those means concept, so automatically your mind transfer from like learning the riding the bicycle to riding the bike or another car, right? So here also in the C++ or Java language, right? So most of the concepts such as like control statement, conditional statements, they will remain same. Whatever programming language you are going to learn, so the concept will remain same. But if you go in different languages such as Python, Java, right? So the way of writing or syntax will change only, right? But the if and else conditional statement, they will remain the common, right? How to create the function, the name of the functions, printing statement, they will change, means for the different languages, but the concept will remain the same. So all those common property, basically you can transfer, your mind automatically transfer from C++ language to the Java languages. Okay, so that is basically we call it as a transfer learning, right? So of course, like when you learn some game, right? If you are very perfect in one particular game, and suddenly if you start learning some another game, right? So of course, like compared to other person, right? You will take less time because most of the syntax, like how to move, click, all those things will remain the same. Okay, so that is basically the transferring the knowledge from one particular domain to another domain. Okay, so now here you see, so I hope so you have already seen the convolutional neural network model or neural network model. So this is basically the neural network model, right? So this particular architecture is a one kind of convolutional neural network model, and these models you have trained from some digit data set. Okay, so now you can see, so this particular model you have trained from the digit data set, and then if you are this trend, once the model is trained, and if you are testing some other data set such as fashion data set, so basically this fashion data set contains some clothes kind of images, and this digit data set contains some digit related data set, right? So what you can do, so same model, this model, all the weight and bias, they are basically trained by using this digit data set, and then you are transferring, means you are the weight and biases which are already learned, and then you are transferring, means you are testing, right, on this particular task or this particular model, right? So then you can say, means because right now if you don't have any label images of this fashion data set, so you may not be able to train the model. But if you are testing on this particular task, okay, so then you can say if you are getting somehow improvement or somehow like better accuracy if you are getting, so then we can say that you have successfully transferred the knowledge from this digit domain to this fashion domain. Okay, so now here again, right? So here, if you see here, okay, so again, if you see here, so this particular neural network architecture and convolutional neural network architecture, so it is trained by using this digit, and the class may belong from the 0 to 9. Okay, so similarly, so this particular data set also, it also contains the 10 classes like top, trousers, pullover, ankle boot. So all the different kind of cloths basically it is containing. Okay, so here also we can transfer the knowledge from this particular domain to this particular domain. Okay, so basically what you can do. So in the previous example, what you have done. So basically you means what you have done. So the model have already been trained. So this model has already been trained, and you have just tested this fashion data set on this particular trend model. Okay, so here, so let's say sometimes what happens, so you might also have some label images of this fashion data set as well. Okay, so what you can do, right, to get low, if you just test on this particular data set, right, so maybe you may get around 4% and 5% accuracy something, right? So you may not get more than this particular, because this kind of this model has not yet been trained by using this fashion data set. Okay, but what we can do, so you can also, fine tune this particular trend model, okay, from this particular fashion data set images as well. Okay, so now if you see, so different, like how basically further you can improve the performance of the model. So now you take this as it is architectures, right? So this model has already been trained. Okay, and then what you can do, either all these layer, convolution layer, pooling layer, okay, all the fully connected layer. So these models, these layers, you can freeze. Okay, so you are not going to update the weight and biases of all these basically the layer. Only what you are going to do, so you are going to just fine tune the output layer. Okay, so this is basically your output layer. Okay, so here also, so if you do this thing, so that is the also one way of improving the performance of the model, right, or transferring the knowledge. Okay, so here, so you can take the sum of the images of this fashion data set, okay, and you freeze all the layer except the output layer, and then the weight and biases, okay, W and B of the fine tune of this output layer, you can fine tune. Okay, fine tune means from which data set? From this fashion data set. So here also, that also practically we will see that, further how basically you can improve the performance of the model. Okay, so how further you can improve the performance of this particular model here. Okay, so this is the one way. Or another way is you take the as it is architecture. Okay, so this architecture you take as it is, you copy the same replica, you take it here, but the weight and biases of this particular architecture have already been trained from this digit data set. And then what you can do, so instead of like fine tuning the output layer, so what you can do, you can fine tune all the layers. Okay, so that is the another way of transferring the knowledge, or you can further improve the performance of the model. So these are the different ways and different scenarios, right? So you can perform, or maybe some half of the layers, like top layers only you can fridge, okay, bottom layers only you can fridge, and some intermediate layers also you can fridge, right? So it depends on how much data you have and what kind of task basically you are having. So based on those scenarios, you can you can train the model, or you can fine tune the specific layer of your deep learning or convolutional neural network model. So these are basically the different scenarios, how basically you can transfer the knowledge from one domain. One domain means like from this digit data set to this fashion data set. Okay. Okay, so here also what you can do, here also some technique also you can take, like for weight initialization for training this particular model. Okay, so when to use, when like so now one question is like, will it always be possible that the knowledge can be transferred from one domain to another domain? So the answer is no, right? So the task, from one task to another task, from where you are transferring the knowledge, they somehow they should be relevant. Okay, then only the data can be, then only the knowledge can be transferred from one task to related task. If they are very different data set, right? And then if you would like to take that particular model, and if you try to transfer the knowledge, then it might be possible that there would be the negative transfer. Okay, so in that case, it might be possible that the performance may also decrease. Okay, so let us assume that you have some Gaussian distribution data, right? And this neural network model you have trained, okay, from this Gaussian data. Okay, but Gaussian data, nothing is common. This from Gaussian data to this your fashion data, right? So it might be possible that from for this particular case, there would be negative transfer, or the knowledge may not be transferred. Okay, so this could be the scenario. So the means if I say you that can the knowledge always be transferred from one task to another task, then the answer is no. It depends. Okay, so what kind of tasks basically are there, and is there anything which are common, right, which can be transferred from one domain to another domain? So as I talk to you, right, so from from learning from C++ language to the Java language, right? So what are the common tasks are there? Means the conditional statement, control statements, they are basically the common in both the scenario. So definitely those things can be transferred from one knowledge, from one domain, means C++ language, to the Java language. So similar case, like you have to find out the from where, like from which domain to which domain the knowledge can be transferred. Okay, so in this case, the knowledge may not be transferred. Okay, so why is transfer learning then useful, right? So transfer learning basically allows you to leverage huge data set and existing model to solve new problem, right? So if I talk to you, right, so let's say if you are going to build some application, okay, some object classification application you are basically the building. Okay, so let's say you have a very few images. Let's say only you have a 200 images. Okay, and you have a 20 classes. So 20 classes and 200 images. For each classes you have collected 10 images, right? And you would like to develop the model. So let's say this is the CNN model you have taken, right? And then if you would like to train this particular model, so you have a very less images here, right? So it might be possible that your model may be underfitted. Okay, if you try to train this particular CNN model from scratch by using this 200 images of 220 classes, so in this case the model may be underfitted. Okay, so what you can do then, so another way is, again you have to collect the more and more number of images, and then you have to annotate them, because right, when you are going to train any convolution neural network model or any supervised learning algorithm, so you have seen that two things are required. Okay, if you are trying to train the model, so let's say CNN model, right? So two things, what are the two things? So feature space along with the means their label. So both the things you have to combinedly you have to give, then only you can train the model. Okay, but collecting this, annotating this is a very hectic and time consuming task. Okay, so then further what you can do, so the another way is, so why not you can use the concept of the transfer learning. So in the case of the transfer learning, basically what you can do, so you can download some pre-trained model. So some, like, image, some model, let's say some architectures you have already seen, right? ResNet is also the one kind of convolution neural network model, and that particular model you have downloaded. Okay, and then this model means what happens, so this model have already been trained, okay, by using the ImageNet data set. So there is a very large ImageNet data set is there. Okay, so it contains around like 1000 classes. Okay, and then the number of images may be around like 1 lakh or 2 lakh, something more than 2 lakh images there. And then with the help of these 2 lakh images, okay, and this ResNet model has already been trained, and all the weight and biases of this particular model, they are trained with this 1000 classes of these images. Okay, so now this has already been trained, and then what you can do, so just download this trend model. Okay, so this ResNet model, you just download it because model has already been trained with very huge data set. Okay, the huge data set means ImageNet data set. Okay, and then that weight and biases, you have already the same weight and biases you have taken here. Okay, they are trained already by using the ResNet, by using this one means a big huge amount of huge data set. And then what you can do, you can take these 200 images and then you fine tune it. So then you will see the earlier, if you take like simple neural network architecture, so if you are getting around 20% or 30% accuracy something, right? Instead of this thing, if you take this pre-trained model, so we call it as a pre-trained model, right? So which is already, this model has already been trained by using the ImageNet data set, and you have just fine-tuned. Okay, how you can fine-tune? Either you can fine-tune all the parameters of this ResNet model, or just means output layer also you can fine tune. Okay, so you will see, if you do this thing, then you may get around 70 to 80% accuracy. So 20 to 30% improvement basically you may easily get. Okay, so that is basically the advantage of the transfer learning. So what is the reason? Okay, what is the reason basically this huge improvement is there, like 20-30% improvement is there? Because see, you have a very less images, right? So from these less images, it might be possible that your model may not be learn the whole property of the images, means side corner, color combinations, ages. Okay, from these 200 images, the model may not be learned, but definitely the images which you have collected of these 20 classes and the 1000 classes, so some property, okay, maybe age, brightness, colors, okay, so all those properties may be common. Okay, so that's why the model have already learned how to identify the age, how to identify the color. All those properties have already been learned by this ResNet model when you trained it from this 1000 classes of this ImageNet data set. So here further it has not to learn here, because already you are using this pre-trained model. Okay, so just whatever the objects are there, so this model may concentrate only on learning the what are the new things are available in this particular object. Okay, so because of that, you may easily see there is a huge improvement in the performance. Okay, so here this is the one thing. Now second is fine tuning existing train model to your unique data set. So same thing, whatever concept I have told to you, the same thing, right? So deploy models quickly and with limited computational and data sources, right? So of course, like, so what you can do, so you have a very big data set, you have fine tuned the model, okay? And then once the model is trained, so that particular model you can deploy in some edge devices. Okay, so maybe let's say you have trained one particular model for disease recognition. Okay, disease, different types of diseases can be recognized of agriculture or agriculture. Okay, So that particular now what you can do, so that pre-trained model you can also deploy in your edge devices such as your smartphone, okay, your your tablet or any other edge devices. Okay, so then you need not to fine tune, and then this trained model can be utilized for recognizing or real world application as well. Okay, so when is the transfer learning appropriate? Okay, so when basically we use the transfer learning. So your problem, so I told already, right? So always it is not possible that you may always transfer the knowledge from one domain to another domain. So if your problem is similar to the problem that someone else has already solved, okay, and publish their model. So like I already told, right? So one model like ResNet model, and so it is for basically the object classification, right? So 1000 different objects can be classified. So they have already trained, right? And then similar again, like similar kind of images you are taking, okay, and you are trying to classify those things. So in this scenario, because the similar kind of task is there, so definitely you can use the transfer learning. Okay, the model was trained on a lot of more data than what you have. So another case like earlier I already imagined data set contains more images like 1 lakh, more than 1 lakh images, and you have only 200 images. So in this case also you can use. And another one is the model is deep. Okay, and of course like when you are going to have the bigger model like ResNet, VGGNet, okay, so different architectures of the model, so definitely this will work. Okay, but in the case of the shallow models like which has very few layers few layers, right? So let's say you are going to develop a model which has like only 2 and 3 convolution neural network convolution layer. Okay, so in this case it might be possible that, okay, so very less these shallow model are likely to transfer the knowledge. Okay, so that also will be possible. Okay, is transfer learning appropriate here? Yes. So when the transfer learning is basically the appropriate, so fine tune the AlexNet to distinguish different model on BMW, right? So means can you use like some AlexNet model which is already trained by using the imaginary data set, right? So if you fine tune that AlexNet model to distinguish the BMW cars, like some images are there. So is the transfer learning appropriate here? Then the answer is yes. Okay, so definitely. So there is also objects, shapes, like colors, all those properties are also there, like in the ImageNet data set and also in this BMW data set. Okay, so definitely then the transfer learning approaches may work. Another is fine tune AlexNet to predict credit card fraud. Okay, so will it be true? Yes or no? How many are saying yes or no? No, right? So definitely no. Why? See, so fine tune AlexNet model is basically the convolution neural network model. Okay, definitely this model is based on the some images, right? But credit card prediction, right? So some numeric data may be there, like so how many, whether he has paid the all the installment, okay, how many times like he means he has not installed the installed means like whether he has settled his installment or not, right? Whether he has paid or not, he is maintaining or not, right? So what is his CIBIL score is there. Okay, so all these are the numeric value. Okay, but the model has already been trained by the convolution neural network, so it will be difficult. Okay, so then here using this transfer learning may not be appropriate, then it may be wrong here. Okay, then another train a model on US housing sales data and then fine tune that model to Indian house sales data. Okay, so the here the answer may be different. May sometime may work and sometime may not work. Okay, so let's say if you have trained the model, right? So US housing sales data, right? So of course, and if you test it on the Indian housing sales data, right? So then definitely it might, sometimes it may work, but most of the time it may not work, right? So because you already know, right, the US housing sales data, right? So definitely the cost of this US housing sales may be much, much larger, okay, compared to the Indian housing sales data, right? So then there may be the biased, or there may not be the, might be possible that the model, if you test on like if you give the size, square size, like area, right? So how many, whether it is a 2 BHK, 3 BHK, and in which area it is, right? So of course, like if you give all these property and then if you predict what would be the price of that particular house in US, so definitely the price of the house in US much, much larger than the Indian house price. Okay, so in this case, it might be possible that your model may not give you the misappropriate or correct result. Okay, so now then how basically you can use the transfer learning? Okay, so first you have to decide whether it is appropriate. Do you have insufficient complex data, right? So in the previous scenario, I had 20 classes, and each class contains the 10 images, so 200 classes. So definitely I was lacking the label images, right? So in this, it means insufficient complex data. Okay, so does a well-trained model exist? So I need to check whether is there like similar kind of is there any well-trained models are available? Yes or no? Yes. In my case, it was available. So I had taken the ResNet model, which was already trained on the ImageNet dataset. Okay, so these are the scenario you have to basically check. So then another scenario, like decide which layers to freeze. Okay, so it is not necessary that all the layers you have to freeze. Okay, and you have to fine tune all the layers. Okay, it depends like which fridge, like you based on your intuitions, right? Which layers you would like to fridge and which layers you would like to fine tune. Okay, so then that after doing this fridging and fine tuning, so the result will be closer to the original data set. Okay, the closer of your data to result model and more layer can be frozen. Then fine tune the target model as much as possible. Okay, so once you have taken the model, you have decided that which layer are to be frozen or which layers are to be fine tuned. Okay, then you try to fine tune the model using the target data set. Okay, then inspect the model and result carefully. Never assume that the transfer will be successful, and you cannot assume all the time that the knowledge means like the knowledge from one domain to another domain will always be successful. Okay, now in this topic, now you have learned about what is basically the transfer learning. So why transfer learning is useful in means deep learning, and when to use the transfer learning and how to use the transfer learning. Okay, so now I will try to reply. So some answer. Sir, how can we know which model is trained on which data set, and how to apply on similar data set? How we will know? See, basically, I already told you, right? So this PyTorch, okay. So they means if you search it there, so they will give you the details of all the fine-tune data set. Okay, from which data set basically it has been fine-tuned. Okay, and what kind of data set it is there. Okay, so that you have to think yourself. Okay, if you see that okay, that the model which have been trained or trained from the data set which is similar to your data set. Okay, so then definitely what you can do, you can use that particular model. Yeah, how to freeze the layers. Okay, so now when I will take the practical, then I will tell to you how we can freeze the any specific layer or entire layer of the data set. Okay, so that I will tell to you. If some layers are freeze, how does the each back propagation happens in that network? Okay, see, if you are freezing means basically for all the layers, basically you are computing the gradient. Okay, so whether it is up to you whether you would like to update the gradient or not. Okay, so in the practical session I will tell to you, right, whenever you are going to means when for each and every parameter, you have a one gradient. Okay, the gradient value may be true or false. If it is false, then what does it mean? The model will understand then the weight of this particular parameter need not to be updated. Okay, so that I will tell to you. What does the freeze means? Freeze means you are not going to update the weight of that particular layer. Weight and biases you are not going to update. That is the meaning of the freeze. Okay, sir, pre-trained models on ImageNet can be used for video and new MNIST dataset. Yes, though that can be used. Yeah, sir, fine tuning means optimizing. Yes, fine tuning means optimizing. Sir, pre-trained model on ImageNet can be used for video. Yes. Yeah, sir, it is like studying computer science engineering and writing the exam in electrical engineering. How is it possible? So, see, you have to identify, that what are the common things in both computer science engineering and electrical engineering. Okay, so it might be possible that in the first year, so you might have some common subjects. Okay, and like C programming, you might be having electronics. Okay, so those subjects are also taught to the computer science engineering and electrical engineering. Okay, so from that perspective, you can see still some knowledge can be transferred from one place to another place. Before applying the same weight, are weight and biases not a function dependent on input? No, weight and biases are different. So as I told right in the beginning, also I told you right. So initially, so the weight and biases we assign randomly. Okay, then with the help of right your data, you are going to update those weight and biases so that the output will be same as what you are expecting. Okay, so that basically you try to do. Okay, so now coming to the second topic, okay, MNIST to fashion MNIST. Okay, so how basically in this topic, so in this topic you will learn how to implement the transfer learning in PyTorch and how to copy models parameters. Okay, so that basically I'm going to tell you. Okay, so in this scenario, what I'm trying to do here, so this is the MNIST data set, right? So this MNIST data set basically contains the digit 0 to 9. Okay, and this is the fashion MNIST data set. Okay, so it basically contains the different varieties of the cloths. Okay, so here first what I'm going to do, so I'm going to first train the model from this MNIST data set. Okay, so from this MNIST data set, I'm going to fine tune, and then I'm going to transfer then I will take this same architecture and then accept the output layer. I am going to fine tune this one. Oh, sorry, I'm going to fridge all the layers parameters. So all the weight and biases of all the layers, they will be frozen. Okay, and then only the fine tuning will be done on the output layer, on this particular layer. Okay, from this fashion MNIST data set. Okay, so that basically I'm going to do it here. Okay, so now see, as usual, like we are going to import different libraries, right? So NumPy, right? So import NumPy as NP, import torch, right? And import torch.nn for constructing the neural network model, right? And then function, like, so there are some functionalities like softmax functions, all those kind of functions are available. Then torch.utils.data, right? So here for basically you are going to feed your data into the your convolutional neural network model in some batch wise. Okay, so with the help of this data loader and tensor data set, you can feed your entire data as a batch wise. Okay, so for that particular, I have imported these two classes libraries like data loader and tensor data set. Tars vision, right? So Tars vision, right, for performing the transformation or like cropping, and normalizing. For that purpose, you can use. And Tars vision also contains some pre-trained models, okay, like ResNet pre-trained model, and some other models are already there. Okay, so that models directly you can import from this Tars vision library. And then from sklearn, this sklearn dot model selection and train and test split. Okay, so here basically the data set you are going to split into the training set and test set. Maybe if you have 100 samples, okay, so if you want to use 70% data set for training and 30% so for testing, so randomly it can divide it into the training and test data set. Import copy. So import copy, basically we are going to use for the purpose of uh, copying the parameter of from one model to another model for that purpose. Okay, and then you usually you already know these libraries. Okay, so now coming to here, so data preparation function. Okay, what is basically the data preparation function? So here I have defined two functions here, like load MNIST, okay, data, and the load fashion MNIST data. Okay, so this particular function basically is going to load MNIST data set. So this MNIST data set basically contains 0 to 9. Okay, remember, so this MNIST data set contains this MNIST dataset contains 0 to 1, 2, dash 9 digit. Okay, so this is basically the data set. And then another data set also we have taken. So this particular load fashion data set contains like means 10 classes. Okay, like that you have seen here, right? Like top, trousers, pullover, ankles. So these many classes are contained by this particular data set. So load fashion MNIST. So how you can load? Okay, so basically this MNIST data set is already available in NumPy. Okay, so you can load it. So np.load txt, and you have to just tell. Okay, so here you have given the path. So then this data can be downloaded directly. Okay, so it is already available in the NumPy library, this particular data set. And then you can load this particular data set and then labels. Okay, so now the data set, like first column basically belongs to the label, and rest of the columns belongs to the features of and pixels of that particular image. Okay, so that this image is basically the size of this image. You will see that grayscale images. Okay, and grayscale images, and the size of the image is 28 cross 28. Okay, so then how many total pixels will be there? So 784 something pixels are there. Okay, and then first column and rest of the column basically they belong to the image feature, and this first one may belong to the level of that particular. So whether it is a zero image, one image, or two image. So that's why you have taken it here. Okay, so now this is done. And then here you see, because all the images, if you see, right? So like this is like this. Okay, so here all the columns. So here, so this is the zeroth column. So here the labels are there, like let's say one, the 1 digit, the 2 digit, 0 digit. Okay, so the rest of the, this is basically the total 784 pixels are there. Okay, for each column. So corresponding columns, all these remaining values basically belong to the these many pixels. Okay, so now then you are normalizing your data and then image dot reshaping. So what does it mean? What you are trying to do? So then because it is in 2D, so now then you are going to convert it into the 28 cross 28. Okay, so then here you are trying to do it here. Okay, so then trend test split. So image labels test size. Okay, so means test size means how many percentage you would like for training and testing. Like by default here 0.1 is written. So what does it mean? So you are giving the whole data to this trend test split, and then 90% data will be used for the training and 10% data will be used for the testing. So then the data has been divided into the training and testing. Okay, so trend, X test, Y trend, corresponding labels. Okay, now the data you have divided. Okay, now this data in a NumPy, right? Now what you want basically this data. So you want it in a tensor, okay, to tensor data set. Okay, so that's why what you have done. So again, you have clubbed together this trend, X trend and Y trend, okay, in one form. So tensor data set. So now you have created the tensor data set, okay, and also you have created the test data set as well. Okay, so now their entire data is there, like many classes are there, like 40-50,000 images are there, right? But at a time you would like to extract, or you would like to take only 30 to 32 images and per batch. Okay, so that's why you have to tell the at a time when you are going to take the images from this pool of images, then how many images you would like to take. So here you can define the batch size. So usually 32 batch size you take, or 64 batch size you usually take it here. Okay, once if you give, so now this is your data loader, and similar for the data loader for the test data set. So both basically you are returning from here. Okay, so same thing you can do for the load fashion MNIST data set, right? So this data set basically available in the Torch Vision library. Okay, so now you have to go Torch Vision dot data set, and then you have to give the name of that particular data test, and then you just dot slash data. So then this fashion data set, so it basically contains the 10 classes. So these 10 classes will be downloaded, but at the same time what you basically want, you want to convert these images into some tensor, as well as you would like to normalize. So that's why here one there is a transform is there dot compose. Okay, so here also, like if further if you would like to crop the images, you would like to resize the images. Okay, so those parameters you can pass inside this compose. Okay, so when downloading these images, so automatically all these transformation will be done. Okay, so that's why, because transform is equal to, you have given transform. When you are going to download the data set, if you would like to stretch the images, you would like to compress the images, you would like to normalize the images. Okay, so you can define in this transform, and then you can pass as a this argument, and then when you are going to download the data set, then it will automatically done, and then this transform data will be downloaded. Okay, so further, like you group this trend data, okay, here, okay, and then pass to the data loader, so that in batch wise, like 32 32 64 64, you can download the data from here. Okay, so now the pre-processing part is already done here. Now the model definition, coming to the model definition. So let's say I am going to develop a simple neural network model, right? So which you have, 1 minute. Sir, please tell reshape. Yeah, so here reshape means, tell me, see, as I told to you, right? So you have a data set like this, okay? So, some pixels are there, 1, 2, 2, so 784. So these many are there. See, they are in 1D, right? So this is the 1D you have stretched because when you are storing, right? But if you would like to plot these images, right? So if you would like to show these images, right? So again, you have to convert it into the 28 cross 28. Okay, and into 1 if it is a grayscale images. Okay, because if you multiply, then one stretch you can do. So that's why here image dot reshape, and then this means how many channels are there. Okay, so because grayscale images is there, all the images are grayscale, that's why 1 you have written, and then 28 cross 28, because the total size you can see 784 pixels are there. Okay, so then it can be rewritten in the form of like image. Image is basically the 2 dimension, right? So now you have stretch all that means 28 rows and 28 columns are there, right? When you talk about the image, but when you are going to store it, so you stretch all the images, okay, in a 1D. So then there would be 784 pixels will be there. Okay, so then again you are going to reshape them. And then why the -1 is there? The -1 means, like, when you are going to give the data. Okay, so maybe 10 images at a time you are giving. Okay, so -1 means whatever the size is there. So how many images? Let's say you have a, so this is the 784, 784, 784. So 10 images are there. Okay, so then how many images are there in this particular, so 10 is there. Okay, if you take the minus, so automatically it will take the 10. Okay, you don't know what is the size of, like, how many images are there. Okay, maybe 10,000 images are there, 20,000 images are there. You don't know, right? So then what you can do, if you don't know, right? So you can write the -1 here. So whatever images are there, so whatever the number of rows are there, it will automatically extract. This minus will extract. If there are 50,000 images are there, so automatically this value will be set to 50,000. Okay, so usually we write the -1. If you don't know, you can just write. You can also write, if there are, if you are sure that there are 50,000 images, so directly you can write the 50,000. If you are not sure that how many data set, how many images are there in the data set, so simply you can write the -1. Okay, so now let us talk about the model definition, right? So definitely one neural network model yesterday, first we talked about like different layers of the convolution neural network model in the first session, and in the second section, Purnima Singh, she implemented how basically you can implement the convolution neural network model, right? So that basically we had seen in the last class. Right. So now today I am just going to define a simple neural network model. Okay. So this neural network model, basically what it is going to contain. So it is basically going to contain, so two convolution neural network. Okay. So two convolution neural network are there, and then two fully connected layers are there. So these are the two fully connected layers are there. And then definitely you are going to pass some, this is a CNN convolution network. This is the CNN, and this is the fully collected layer, and then this is the fully collected layer. Then there is the output layer. Okay, so then okay, so now see, so now you know, right? What is the input size? What is the input size images basically? So what is the input size? Can you tell me what is the size of the image? MNIST digit data set. I told you, right? So 1 cross 28 cross 28, right? So this is the basically the size, right? So when you are going, so this is this image basically you are passing through the convolution neural network, right? So when you are going to create the convolution neural network, so then there is a function in the neural network which you can call. So CONV 2D, because this is the 2D convolution neuron. There is also the 3D, 1D is also there, right? So 2D is there. So what simply you can do here, okay, so you can call this function. Okay, so remember first argument what you will have to give it here. Okay, so you in the last class you might have seen, so this number should remain same as the number of channels. Okay, so now you tell me in this MNIST digit data set, how many channels are there basically? How many channels are there? One, yeah, definitely. So one channel is there. Okay, so then this first argument should be 1. Okay, so this first argument should be 1. Okay, now second one is, then the second argument means after performing the convolution, okay, then how many feature maps you want. Okay, after performing the convolution, so you might have seen in the last class, right? So let's say if you want 10 feature map, and this second is basically going to tell you then how many feature maps are there. Okay, so then these many kernels basically you have to take. Okay, because you remember, so this is going to tell that how many features you want. So right, so then that many kernels, different kernels you have to take. Okay, so if we talk about like 200 feature map you want, okay, or through 200 channels, sometimes we can say channel. So then you have to take so these many kernels, and then each kernel is going to produce one feature map. Okay, so that's why this 10 is basically going to define you the feature map. Okay, then this is basically the kernel size. Okay, what is the size of the kernel? So as you know, your input images is, what is the size of the input images? So 28 cross 28. Okay, and then what is the kernel size here? The kernel size is 5 cross 5. Okay, then this kernel you are going to convolute across this 228 cross 28 images. Okay, so then how many kernels you have taken here? 10 kernel. So each kernel is going to produce one feature map. So one kernel of this side going to produce one feature map. Another kernel. So then there will be how many features map would be there? If you are taking the 10 kernels, if you are taking the 10 kernel, then how many features map will be there? 10, definitely. Very good. So 10 kernels or 10 features map basically you are going to take. Now my question is, so let's say you are this is the like 28, right? So this is the 28 cross 28 size of the image, input images, and then kernel size is 5. Okay, now like each kernel, so let's say first kernel, so they are going to produce a one feature map. Now you can tell me what is the size of this feature map? What is the size of the feature map? What will be the size of the feature map? So yesterday you have seen, right? So the definitions, right? So n minus res, n minus k plus 2p, sorry, 2p divided by s plus 1, right? So now you see what is the n here? 28. What is the k here? 5. So what is the padding here? 1, right? And then s is basically 1. So 28 minus 5, 23, right? Plus 2, 25 and plus 1. So then what is the size of this feature map then? 26 cross 26. Okay, then the size of this feature map is basically the 26 cross 26. So here also you can see we have written here. So 28 into 2 into 1, right? Minus 5, right? Kernel size, and this is the padding, and then stride, and then 1. Okay, so then this convolution layer, again, I am passing with the one pooling layer. Okay, so then again it will be divided. If you pass by one pooling layer basically try to reduce the dimension of your feature map. Okay, so divide by 2 you are performing. Then if you pass it by the pooling layer, Okay, then two pooling you are taking. So then the size of the output map would be 13 cross 13. Okay, so now you tell me, now then what is the size of this output then? So 13, this is the size of the images, 13 cross 13, right? And then how many features map, how many kernels you have taken? 10. Okay, so that's why this 10 will come here. So these many features map will be there. Okay, so now again you remember, so whatever the number of features map or number of channels you are taking, so that output will remain same. Again, if you are going to take the convolution layer or any other layer. Okay, so now again second convolution neural network you are taking it here. So nn dot con2. So then this number, because you like the feature map, your feature map contains how many channels? 10 channels. So that's why this number will remain the same. Remember, okay? And then again the size, again what you are trying to do, so you are going to take the kernel size. Okay, then the kernel size you are going to apply here. Okay, so then what will be the kernel size here then again? 5 cross 5 into 10. Okay, so that much big kernel size you will apply on this particular convoluted output. Okay, and then here you are taking the 20 kernels. Okay, so then again 20 kernels will be there. Again, if you pass on this one, 13 plus 2 minus 2 into 1, 5 and 1. Okay, so then the output is going to be 11. So the output of the feature map is going to be the 11 cross 11, and then divide by 2 means again you are performing the pooling, and then the you are left with this 5. So then the size of the feature map is going to be the 5 cross 5 into 20. Okay, remember into this 20, because 20 kernels you have taken here. Okay, so now yes, 20 into 5 cross 5. Yes, true. Okay, so now then self.fc. Okay, now what you will have to do then here, so you have to this is the means you have to stretch all these features 20 cross 5 into 5, and then you have to so that's why you have to, then you are left with this 20 cross 5 into 5. Okay, so these many outputs are there. Okay, after the performing the convolution, okay, and pooling, and then you are going to add the fully connected layer. Okay, so these many outputs are there. So how many outputs are there? 20 cross 5 cross 5. Okay, so in order to receive all those output, so you have to take that many neurons in this fully connected layer. Okay, so that's why 20 cross 5 into 5. So these are the outputs are there, and then this 50 means this convolution neuron, this 50 in this fully connected layer, basically you are trying to take the what happened? Isita, are you there?
2996.
Okay, so now after performing the convolution, so two fully connected layers there are there. So these many outputs are there. So you are going to add a linear layer, and that particular layer you are going to add how many neurons? 50 neurons. Okay, then for one more fully connected layers you are taking. So 50 cross 10 means, because since you have how many outputs are there basically? Only 10. So that's why this 10 basically you have added it here. Okay, if there are like 26 outputs are there, so definitely this value you might have taken the 20. Okay, so if I tell you here what has happened here, basically. Okay, so this convolution, once you have performed the convolution, then again you have performed the convolution. Okay, and then there is a feature map are there, right? So earlier the size of the image was 28 cross 28. Then further you have reduced it to the 26 cross 26. And then how many kernels you have taken? So 10 kernels you have taken. So these many features map were there. Okay, further you have taken the 5 cross 5 kernel. So then further you have reduced and 20 kernels you have taken. So 20 cross, and then sorry, then you perform the pooling. So that's why here it will remain the 13 cross 13, because in between you have performed some pooling. Here also in between you have performed the pooling. Then 20 cross 5 cross 5. Okay, so these are the convolution output. And then there is a fully connected layer. So these many output like 20 cross 5 cross 5. Okay, these many outputs are there. Then you are trying to pass here. Okay, so then this is the fully connected layer they are there. Then how many neurons you are taking? So 50 neurons you are taking. So 1, 2, so on, 50 neurons here. Okay, then further, basically the URL is the classification task. Okay, so then again this 50 into like 10, you are bringing down it to the 10. Okay, 0, 1, because these many classes basically you have only the 10 classes. So 1, 2, and then 50 classes. Okay, so this is basically the whole architecture of your convolution neural network model for this particular thing. Okay, so now after doing this thing, yes. So just wait a minute where we are performing the pooling. Okay, so okay, now see, so we have defined all this architecture. So after defining this architecture, now see. So this is the like for printing, let's say debug one flag parameters I have taken it here. So if I want that, to print all the architectures or the shape of each and every layer. So with the help of this flag, you can print it. Okay. So now see, first you have come like forward pass. Now image has come. Okay, so 128 cross 28 images has come, and then you have passed first through this convolution layer. So now you are passing through the convolution layer, then immediately pool to see the max pooling you are performing, right? So let's say the output images was 26. The out feature map was there. So the size of the feature map was 26 cross 26, right? So max two pooling you have performed, then it is divided by the 2. Okay, 30. So now then after passing this result, then you are passing to the ReLU function. So see here ReLU function. This is the first convolution layer. Okay. Then the output of this first convolution layer, then further you are passing to this con2. Okay. So then again you are performing the max pooling here, and then again you performing the ReLU activation function, right? So I already told, right? So for performing the non-linearity, so some ReLU activation functions you are performing. Okay. So now here then x dot size. So you are going to write how many features basically are there, and -1. So whatever the size are there, okay, let's say 20 cross 5 cross 5. So then this view, so whatever the size is there, so this will be converted into this, means it will be stretched. So it will be stretched. Okay, so this is going to stretch. So 25 means 100 and 500. Okay, so then if you perform this stretching, so earlier the data was like this in the vector form. Now x dot view you have written. So then it is stretching. Then stretching means this 500 will come. And then you are passing it through that fully connected layer 1. Okay, so then fully connected layer like 500 into 50. Then further the output, 50 output are there, then you are passing it through the FC, fully connected layer 2. Okay, so this is basically you have defined the digit. Yes, yeah, X view will flatten the 2D into 1D vector. Yes, yes, it is flattening basically. Yes, it is performing the flattening operation here. Okay, so after doing this thing, okay, so now you have defined the class basically. Now what you want basically, so when you are going to develop any model, okay, in deep learning, so three things you have to remember. First is defining the model. So now you have defined the model. So this model you have already definitions you have already given. Okay. Second thing is so loss function. Okay, you have to also which loss function, whether it is, I told right, whether it is a categorical data. If it is a critical categorical data, then you have to consider the cross entropy loss function. And if it is a continuous data, then you will have to take the mean square error loss function. Okay, but since this is the categorical, you have to categorize whether it is a 0, 1, 2 or digit, or the which fashion belong to top, skirt, or whatever it is there. Okay, so then three things. So model definition. So model you have defined. Second one is loss function, and third, because now there are many parameters are there in this particular model, right? And what basically you want, so you would like to optimize all these parameters. Okay, so how basically you can optimize these parameters? So in order to optimize these parameters, right, so you have to use some uh, gradient descent approaches, like earlier we talked, right? So gradient descent approaches we talked about, right? So gradient descent approaches, like either you can compute the gradient of all the data. So let's say if you have a 50,000 images, right? So gradient descent approaches will take all the data, 50,000. Okay, but it will be very complicated, right? So you may not be able to compute. So then there is a mini version of the gradient descent approaches is available, like stochastic gradient descent. So batch wise gradients you can take and you can optimize, right? So dot optimizer. So different kind of optimizers are there, like gradient descent optimizer is there, Adam optimizer there, right? So different versions are there, so you can take it. Okay, so then model dot parameters. So when you are going to write this model dot parameter, so means all the parameters, like all the weight and biases of your convolution neural network models will come. Okay, and then you are passing, because something you would like when you are going to define the gradient descent approaches, right, stochastic gradient, so it want the parameters, which parameter you would like to optimize. Okay, and at what rate you would like to optimize the parameter, like weight and biases of this model. Okay, so that's why learning rate also, or you can call it as a step size, so that also you have to pass, right? So, sir, can we use any other method also for back propagation? Yes, definitely. Here the Adam optimizer is also there. So lot of optimizers are there. So that basically you can use. Okay. So how to use which optimizer? So it totally depends on your intuition. So how many times you are running the program, you check it. Okay. So the behavior, you try to recognize the behavior of the data, right? What kind of data is there? Is there so much non-linearity is there, or it is a means like a totally convex function, non-convex function is there. So it totally based on the property of the data. Okay, so which again you try to run and you see, like if you are getting more accuracy with some other optimizer, right? So definitely then that data is suitable for that particular optimizer. So that is your basically intuitions and your practice, how much you are going to practice on it. Okay, so now here that model. So three things you remember. One is model definition, loss function, and optimizer. Three things are important. Okay, so now how basically you can train the function. Okay, so now before telling to you these things, so let me tell you some important points here. Okay, so that how basically you have how you can fine tune the model, how you can extract the some model definition will come outside the class. So this is totally model. This is totally model. Either you can through the class you can do it, or you can function also you can write it. It depends on you. Okay, so here see this class I have defined, and then I have created the object. So this model is basically the object here. So when I'm going to call this particular function, so this function is going to create the object of the class or object of your model, and then loss function, object of your loss function, and optimizer. So three parameters basically it is going to return to you. Okay. Okay, so what I can do here, so let me tell you, like, how basically different models you can, mm, okay. So now how basically you can train the model. Okay. Okay, before training the model, so let me just tell you about something. So now you have already created the model here. Okay, let me call this particular function. Okay, let me define this training function, or okay, so now I am just initializing. Okay, so I am going to create a one particular model, MNIST model, and then loss function. So just by calling this particular function, so instances of your this digit CNN model will be created, and the instance of the loss function and optimizer. Okay, so now this, let me do it. Okay, so now you would like to see the model. Okay, so what you can do, just you can write MNIST model. Okay, and then you would like to see all the parameters of this particular model. So you can see, right? So all the properties like digit CNN, this is the convolution, right? 1 cross 10. So 1 is the channel, right? So grayscale, basically if you have given RGB images, so then this value would be 3. Then 10 kernel, and then this is the kernel size, stride, and padding. Okay, so these are all the parameters of all the layers. Basically, they are here. Okay, so now what basically you would like to see the parameters of this particular model. Okay, so then what you can do it here. So for, let's say, param in MNIST. Okay, so then you can see, so what are the basically the sizes of each layer. Okay, so that basically you can see it here. So let's see if you print it here. See, so 10 basically indicating the what? So 10, what basically it is going to indicate? So these are the basically the convolution layers when you are going to follow it from here. So these are the output size of each and every layer, okay, which are basically shown. If you would like to print, right? So And if you would like to see, yes, 10 is output layer, means how many channels you have taken basically. Means 10 means like earlier, how many channels is there, right? 10 means kernels, yes, feature map. Then 20 you have taken, then 50 you have taken, right? Then then this is the output, then the 50, then the 50, these basically second entities is telling the biases. Okay, and if you would like to see the actual value of this one, so you can see like param. So the value, all the values, like what are the weights? So these are basically randomly assigned, I told, right? So yes, 50 is the hidden neuron. Yes. Okay, so you can also see the all the values of the parameters from here. Okay, so that is done. All the layers parameters. Okay, so let me tell you one more thing here. So you would like to see that which parameters belong to which layer, which convolution layer. Okay, so then this can also be done. So for name param in MNIST model dot named par. Okay, so if you do this thing, this value it is printing. See, so here you can see convolution layer, like two things are there, right? So basically the weight is there and biases is there. So as you have seen in the last class also, right? So this is basically the weight, and then so for each feature map, one biases will also be there. So there will be 10 biases are there. Okay. So now what is the size of each convolution layer and what are the biases are there? So then if you would like to see, then you can see by using this model dot named parameters. You have to write it here, so then it will print all those outputs here. Okay, so now these weights, like if you want to print, so just print param you have to write, so then all the values will be printed. So let me print here. See here, along with this output, see this particular input of each layer. This is the one tensor, right? So there is also one more function inside required grade is there. Okay, so this required grade, basically what you, by with the help of this required grade, you can fine tune the parameters value, or you can fridge the parameter value. So right now, so by default, this requires grade parameters value are true. Okay, so what does it mean? Then these weights, okay, these values can be updated, okay, and or can be fine tuned. If you make it false, okay, so then you are freezing that particular layer. Okay, if you are making it freeze, if you are making it false, then you are freezing that particular layer. Then in the future you may not be able to train or fine tune that particular layer. Okay, so with the help, this is very important. So for every layer, okay, so that parameter was be there for this particular this is basically for what, a fully connected layer, biases is there. Okay, so now you can see for the biases, like also this is there. So either you can train or fine tune. So for every layer it will be there. So see here it is also there. See, for every layer, for weight and biases, this required grade will be there. And if you make this required grade as a false, so then you may not be able to fine tune that particular layer. Okay, so now then how you can make it a false? So I'm just going to tell you. Okay, so now fridge all layers. Okay, so for param in, yes, see, model parameters I am taking and param dot required. So param dot for each, because this is going to iterate for all the layers of the your MNIST model. Okay, so as you can see how many layers are there basically. you have printed 1, 2, 3, 4. 4 layers are there. So it will be iterated for 4 times. Okay, so it will be iterated for 4 times. 1, 2, so then means like 4 into 8, 8 times for each and every weight and biases. Okay, so then required grade here, it will also be the required grade, here also the required grade, and then one by one you are taking, and then you are making the false. So then what will happen? So then all the layers, the required grade will be false. So if you would like to see whether they have become false or not, so further I am going to see it has become false, right? That's why you are not able to see the required grade. Okay, remember here, because you have made the see the required grade has been disappeared. Okay, you are not able to see because you have made it a false. But again, if you make it as a true, so let's see if I am going to make it as a true. See, now the required grade has come here. Okay, so when it is false, so then all the layers are fridged and you will not be able to fine tune that particular layer. Okay, so now if you would like to see like whether which layer is false or not, so one more way, possible way of checking it. So what you can do, for name param in, okay, so what you can do it here, print name. See, now because you have made true it, that's why it has become true. And if you can make it false, then it has become false. No, no, I am just showing you how basically you can fridge. You have made the custom. So see, pre-trained model means like it is not necessary that someone has already trained the model because they have big resources for running the means model, as well as like they have a big uh, data sets. So it is not necessary that you cannot develop your own model. You can develop your own model also. Let's say you have thousands of images, right? And you would like to give this data knowledge to someone else so that from that whatever work you have done, so they can, so that work will be useful for them. So you can train the model. Okay, so you can also train the model. Okay, and that particular trained model from your 1000 images, you can give to someone else. If some features are common, then further he may fine tune that particular model. So it is not necessary that you have to fine tune the models from some places. Okay, from you download from some other places and then you fine tune. You can also from scratch you can develop your own model or some existing architecture like ResNet, VGG 16, VGG 19, Google Net, inspection, or so these models from scratch you can train, and then once the model is trained, then you can give it to the someone else. Okay, so that you do yourself also. Okay, so I just wanted to tell you that how basically you can do. So same way, so this is the our custom CNN model is there, but same way you can also download some pre-trained model, and then you can work on that pre-trained model. So some layers, if you would like to fridge, you can fridge, and some layer you would like to fine tune, and you can also fine tune. So just I wanted to tell that how basically from this the purpose of like explaining this thing is that how you can see the weight, how you can see that, how you can fridge the layers, okay, and how you can train or fine tune. Okay, so that's why. So this will be same for each and every model. On any model you can access, you can fine tune, or you can fridge. Okay, so now let me make it as a true, otherwise I may not be able to train the model. Okay, so now this is done. Now I want to what was our goal? So we wanted basically to train the model by using the MNIST digit data set, and then wanted to test it on the fashion MNIST data set. That was basically our goal, right? So now you have already defined the model, right? Now you want to training. So training, basically how you can perform the training here. So this train function is going to take the what is the model. So like custom model you have already defined. Okay, to train loader, test loader means training data you are going to give. Yes. First you have to train the model. Then only you means if it is not, see, there are two things are there. First is if the model you are downloading like ResNet, BGGNet, which are already trained from some big data set, right? So then you just need to fine tune that particular model. But what you can do, the same models you can download also, and you can just model, okay, not parameters. So the still that model is not trained. Then you can train that model from your data set, because see here we have ourselves created the model, custom model. It is not at all trained. Okay, so that's why first I am going to train by using the MNIST data set, MNIST digit data set, and then I am going to either fine tune on the uh, fashion MNIST data set. Okay, so that I am going to do you here. Okay, so now first train model. So data, it is good training and testing data. Loss function also it requires. And optimizer, I told three things: model, loss function, and optimizer, along with the how many epochs you would like to train this model. So by default 10 I have given it here. Okay, so then for each epoch, so some training accuracy, test accuracy will come, and some losses will come. Okay, so now for each epoch, right? So by the 10 epochs it is going to run. So one epoch I have taken, then model dot train. So now the model like it is ready for training. So now it will come into the train mode. Okay, train mode, why it is trained? So sometime when you may also go into the test mode, right? So then again further you have to come on the train mode for again and again running the model. Okay, so then for each epoch, so some losses and accuracies, like for batches you are going to compute it here from the train loader, right? So you are some bunch of, like, let's say the batch size is 32. So 32 images are coming along with their label, and then this is the forward pass, means you are giving the, let's say 32 images you have taken of the digit MNIST, and you have passed through this one. So then it is going to predict the label. So 10 outputs are there, so corresponding to each 32 image you have given. So the some label will come, either this image may belong to 0 or 1 or 2, right? So then that particular label, you already know the original label, y batch, and then y predict, you will compare, and then you will compute the loss. Okay, then you are going to take this optimizer dot zero grade. So what basically optimizer dot zero grade does, so whatever, like each and every epoch you have been computing some gradient, right? So it might be possible that that gradient may also be added while computing the another gradient. Okay, so that's why each and every time you are going to remove that particular gradient or erase or clear the previous gradient. So that's why I am writing optimizer dot zero grade. This y batch is, see, label. Okay, so X batch is future, and the trend loader means 30 to 32 images you are taking. Okay, so like each image belong to which class originally it is there. So that is basically the by batch. Okay, and this is the 32. Okay, so then you have computed the loss, the zero grade, so clear the gradient of the previous layer, and then loss dot back propagate. So what basically this will do, so back propagate, so compute the gradient and then pass it in the all the parameters or back propagate. So computing the gradient and back propagate. Okay, so this will be done, back propagate, pass and compute the gradient, and then optimizer dot step. So what basically this step is going to do, so update. So now you have the gradient and all the gradient have been passed to the specific all the parameters. Now once if you write this optimizer dot step, then the weight of all the parameter with respect to the computed gradient, which has already been passed to the each and every weight, then they will be updated by using this particular line. Okay, so after this, these three lines are very essential. Okay, when you are performing this gradient descent. Okay, so once this is done, so now whatever the loss has come in this 32 images, because the many images are there, right? But let's say 50,000 images are there in your data set, and you are going to take 30 to 32. Okay, so then that particular 32 images, so loss you have computed. Okay, so and you have a epoch, you have taken it from here basically. Then you are computing the accuracy of that particular. So now y predict is there and y batch is there. So you are computing the how much for that particular batch 32 of images. So how much is the accuracy? Okay, then epoch accuracy, then you are going to add that particular accuracy basically here. Okay, now earlier you are training the model. So for all the like earlier you had 50,000 images, and each and every batch you have been taking the 32 images. Okay, once all the 50,000 images are over, okay, all the images are taken, then it will come out of the means like for one epoch you have run the model, all the 50,000 images you have passed through the model. Okay, so now you will come into the evolution mode. Okay, so in the evolution mode means here when you are performing the evolution, then you need not to compute the gradient, because you don't want to back propagate when you are evaluating. Okay, so that's why now you are going to take the testing images. Okay, torch dot no grade means no, you are not computing the gradient, and then you are predicting just forward pass, you have to take it here, and then you see how much accuracy are coming. Okay, so this is for one epoch, and then whatever the accuracy, average accuracy of you will take of all the batches here, mean each then that will be basically treated as the this one epoch accuracy here. Then similarly for the test accuracy, and then the average of epochs of the all the losses. Okay, so these things you are computing, and these parameters you are basically the returning from here. Okay, so this is basically the training mode. Okay, so now you would like to see, okay, so visualize what are the contents are there. Okay, then this loss and training loss and the test loss. Okay, so let me do it here. So far you have not trained the model, so I think no meaning of this visualizing. Okay, now come to here. So model transfer utility. So basically how you can transfer the from one model to another model. Okay, so what basically this function is going to do. So see, there is a source model. Let's say you have source task is basically your MNIST task you are considering, MNIST digit task you are considering as a source, and MNIST fashion you are considering as a target. Okay, so then uh, so let's say this is your model, like so digit model. So you have trained this model, right, from the MNIST digit images. Okay, so once the model is trained, so all the weight and biases are there. Okay, so then all the parameters. So what you can do, so you can, this is your source. So either you have to transfer it to the target. Okay, so same digit you are going to copy. Okay, and then here fashion data set you are going to take, and then you are going to fine tune the weight, whatever the trend models are there, you are copying as it is here, and then you are fine tuning with the help of this fashion data set here. Okay, so how you can do it. So here you see basically what this transfer weight will do. So it is basically transferring the weight from the source model to the target model, like from digit model, like the class you have created, from the digit to the fashion. Okay, so I am just going to embed all the parameters of like source dot model and target dot model, and then I am going to take the parameters, all the parameters of like source and target. So these are the source and target. I am wrapping it in a one zip, and then the copy was function is there. Then what this copy function is going to do, all the parameters. Okay, so like two more instances you can create, right? So once if you call, so see, once if you call, so first you have created this MNIST model. Okay, this MNIST model you have created, right? So all the weight and biases are there, and then you have trained this model by using the uh, by using the MNIST digit data set. Now the weight and biases are trained. Okay, now again what I am trying to do, I am creating the another instance of this one, but this instance is for the, this is the source task, and this is the fashion, same model. Okay, but right now once if you create it, the weight and biases are random value, right? So they are the random value. But what you want in this model, so whatever, because this model MNIST which you have created, now the weight and biases are, they are trained by using the MNIST digit classes. Now this trend value you would like to copy, whatever the value WB are having, so same thing you would like to transfer from this source model to target model. So for doing this thing, so what you can do, so these functions you can use. So from here source dot param means all the parameters W and B will come from this source, and then they will be passed to the target. Okay, so then whatever the value you fine tuned of the digit MNIST digit data set in this model, so the same will be copied in this particular fashion data set here. Okay, so this is the meaning here. Okay, so let me run it here. Okay, so that you are doing it here. So let me. Okay, so now coming the main execution. So how basically you can execute this function. So now you see MNIST train loader. Okay, so this is basically going to load. So functions you have like MNIST data will come, train and test data will come, train loader and test loader you have already defined. and then MNIST fashion data set test, and these things will come. And then initiate model. So initiate model means like you have created the model, then loss, and then optimizer. Okay, so then one instances you have created, and then you are calling the train model. So this train functions you are passing the which model has to be trained. So now this model like MNIST train, then data loader, test and train loader, loss function, optimizer, and for how many epochs basically. So how many epochs basically you are going to give. So right by default 10 you have given. So now 5 epochs you should run it. Okay. So then this model train models is going to return basically train accuracy, test accuracy, losses and model. So right. So you can see train losses, train test losses, and MNIST model itself also it is passing. So now then you are going to plot those results. Okay. So now after doing this thing, so now the model is trained, right? Now what you want, the trained model, so that particular model, this MNIST model has been trained on this MNIST data. Now the same model you are going to take and you would like to test on the fashion data set and test data. So now you are going to take the fashion data set, okay, and then X fashion and Y fashion you are going to take it here. So this data set basically you have taken because from the loaders you can take all the data here, and you are just performing the basically the you are not fine tuning, right? So that's why torch.noGrade, and then the model you are passing instead of giving the MNIST digit data set. Now the same model with the model which has been trained on the digit data set, now you are passing the fashion data set. Then you are predicting it here. Now you will see here after performing that how much accuracy is coming. Okay, here you have not done any transfer learning. Just you means like you have just tested it here. Okay, still like because some instances are same in both the classes, maybe color or text or the size of the images. Okay, so maybe because of that you may get around like 4 to 5% accuracy. Okay, so that basically you can get it here. So you can print the accuracy. Then you are performing the transfer learning and fine tuning on fashion. Now you see, as you are asking that can we only do the fine tuning on some pre-trained model? No, here also one models you have developed which you have trained. Okay, what is that model? The model name is MNIST digit, right? So that is the MNIST model. Now here what you are trying, one instance is like you have created one more model, simple model you have created, right? So they randomly the weight and biases are assigned, so this particular model, and then you are transferring the weight. So this is the source, right? So MNIST model I told, right? So all the weight and biases are basically the trend, right? And then the same weight and biases you are copying from this MNIST to fashion model. Okay, so definitely the fashion model also, like when you have created, but at the time when you have created the instances, at that time the model, the weight and biases of the model were assigned random weight. Okay, so then the random weight, so what basically you are trying to do, your fine tune weight of the MNIST you are copying from MNIST to fashion model. Okay, so this transfer weight, so that's why we have defined both the model you are passing here, and then you are taking the data and just copying the source means MNIST to digit to fashion data set. So here you are copying it here. Okay, so then so after doing this thing, so train the model. Now the model, now when you are passing, so at this time, so in this model, random weights are not there, but the weight which were trained by using the digit data set. So those weights are there basically. Okay. Then fashion data set you are giving, fashion test, train and loader are giving, and you are seeing. So let me just run it for the one epoch. Okay. So now you will see if you from only in one epoch itself, now you will see, so you will get around 70 to 80% accuracy. But if you just give, instead of this weight transfer, if you just pass it here, so you will see that very less accuracy. So, okay, so both the things I am trying to do it here so that it will be more clear to you. Meanwhile, if you have any questions, so please ask me. The model is running, it will take little time. Yeah, if you fine tune false, if you make it false, then model may not be trained. Simple, model will not be trained. What will the fine tuning means? See, so the parameters. So sir, what tell about the, see, so actually ITR, oh, which ITR you are talking? This iteration, right? Okay. So actually the when data loader, so what basically it try to do the data loader. So data loader, let's say if you have a 1,000 images, okay. So then data loader, if you have given batch size is equal to 250, then the data loader will what it will do. So it will divide into the 4 batches of each of size the 250. Okay, so then this iteration automatically, if you would like to take the images automatically, right, 250, so then you have to iterate it. So first time 250 image will come, okay, then again it will be iterated, the next time second 250 image will come, third time three will, so automatically, because 1,000 till 1,000 images are there, so all the 4 batches will come. So that is the meaning of this next or ITR here. So they will combinedly they will do. So all the 1,000 images can be extracted. See, the MNIST just you didn't train the model, just test it. You train the model on digit data set, but tested on fashion MNIST data set. Then you got the 10.04% accuracy. Okay, and then when you fine tune only for one epoch, right, the training accuracy is 69.98% and test accuracy is 77.97% accuracy. Okay, so that much huge in only one epoch. You see the weight and biases which you have taken, right? So the parameters which were trained by using the source model means like digit MNIST data set. So that much accuracy you have got. Okay, if you would like to see, right, what if like if you don't use this training. Okay, so let me just check it here. Okay, so assume that I'm not going to trying to transfer the weight. Okay, so that means randomly from scratch only I have created one another instances of the model, and then just one epoch I am running. Then how much accuracy I am getting? So that also I would like to see. Yeah, I will share the PPT. Okay, so the code will be there. No problem. Yeah, transfer of the weight. So in the deep neural network, so everywhere the weights are there, right? So weight only you are going to learn. The neurons are there, right? So in each and every neurons, there are some weights are associated. So that only you do. So weight only you are transferring. Now you see. Now you see here. Okay. If you train the model, So only one layer you would like to fine tune. So rest of the models, rest of the layers you don't want to fine tune. So only the output layers, only you would like to fine tune. So that is the meaning of like output layer means. So now can you see the difference? Now you see how much knowledge has been transferred, right? When you use the concept of transfer learning. So instead of assigning the weight randomly, right? So you have taken the weight from the MNIST data set, right? So how much the train accuracy came? 69.98%, right? But if you train the model from scratch, then 61.42. So how much improvement is there? Well, when you are considering the train model, how much percent? 8 to 9%. Yes. Okay. In the test itself also you can see earlier, if you without fine tuning, right, means like weight and voice, you if you did not consider, right, means simply like one instances you have created, 74.07% you got. But the weight and biases which you trained from the MNIST data set, right, digit data set, and you have only one epoch you have fine tuned, so you got the 77.97%. So here also 3% something improvement is there. Okay, so now here you can see what we conclude from here. So we can conclude that some knowledge basically you have transferred from which domain, like MNIST digit data set to even without weight transfer, train accuracy has improved. Yeah, that is fine. That may one epoch only you have taken, right? It doesn't mean. But see, my concept is, even though they are totally different data set, right? One is the MNIST data set with digit data set, and another one is the fashion data set. So still some like 3% or 8% in training and testing, you are successfully transfer some knowledge from one data set to another data set. So that is basically the concept of the transfer learning. Okay, so let me quickly tell you the another code. Okay, where you have just you have done the fine tuning on the output layer. See, sometimes why usually we call the fine tuning on the output layer, because see here in the both the source and the target domain, right, means MNIST digit and MNIST fashion data set, you are going to have the 10 classes only, right? But sometimes it might be possible that, so well, in the testing domain or target domain, you may have the different number of classes also, right? Maybe let's say some alphabet. So MNIST alphabet data set is there. So alphabet has total how many character? How many alphabet? 26, right? And if you would like to test it on the digit data set, so it has just only how many? 10 digit only, right? So how like 26 outputs were there, and then in your digit data set 10 output are there, then how you can do it, right? So then what you can do, so you have to modify the layer. Okay, so then you have to modify the layer, means in the output layer, what you will have to do, instead of 26 neuron, you have to keep the same model you will take, but for the output layer, you will means modify that output layer. So instead of having the 26 neurons, so you will take the 10 neurons. Okay, so that is basically in this code. So here basically what you are trying to do in this code, so transfer learning letters to digit. Okay, so letters you already know how many, 26 letters are there, and then you are training the model from this 26 and just fine tuning the output layer of this model while training the new numbers. Numbers is going to have how many classes? Only 10 classes. Okay, so get more experience working with transfer learning and how to fridge the categorization layer in the retraining. Okay, so you can see, so this is the means 26 this model has been trained for 26 letters, but now these models you would like to retrain for the this 10 letters only. Okay, how you can do. So only fine tuning, I am just going to fine tuning the output layer. Okay, I am going to first modify the output layer. Okay, instead of having the in the output layer 26 neurons output, then I'm going to take only the 10. So import both letter and digit, train on letters for 5 epochs, transfer the model to digit, and fine tune the entire model or categorical layer, then the train only one epoch. Okay, so same thing we are trying to do it here. Okay, so I'm just going to tell you because as we are already running off time, so many of you have some other work. So what I'm going to do here, so just I'm going to, it is very easy code. You can easily understand. So same concept, whatever we discussed, same concepts are there. Okay. And only where I have just like where we have to pay more attentions, like how like only one layer we can modify. So that part only I'm going to discuss here. Okay, so as usual, right, you have imported all the libraries and then you have defined the class, right? If GPU execution limit is crossed, so no way, then you have to wait for 1 day. Okay, see, domain adaptation. Okay, definitely I'm going to take one more lecture on my research. Basically, I have been working on the transfer learning and domain adaptation for the last, 10 years, 9 to 10 year. Okay, so domain adaptation is, the sub part of the transfer learning. Okay, so maybe in the capstone project. So at that time, I will demonstrate my research work. Okay, how basically these techniques basically you can improve the performance, like you can extract the knowledge from one domain to another domain. Okay, that I will tell you later. So Day1 adaptation you can say is a sub part of the transfer learning. If GPU execution limit is crossed, how to execute next? Okay, so means again you will be redirected to the CPU because CPU is unlimited. Okay, so you can run 25, but it will take a more time for running it. Otherwise you have to take you means like some you have to pay some amount of money for some amount of hours, like how many hours you can run the task. Okay, so then you have to purchase from the Google also, they have some paid version. So as usual guys, so MNIST classifier, so this is basically the digit class means this is basically your data set, right? Class, which convolution neural network class, you have defined it here. And here basically in this class, as you can see, output layers. Okay, so just here you pay attention on the output layer. So output layer, this is basically the output layer. So since you have a 26 classes in your data set, so that's why you have taken here 26. Okay, so rest of the things are the same. Okay, so let me define. So now again here what you are trying to do. So this is just tuple means like for the hinting like what basically this particular function is going to give the output. Okay, and then you have created a model of MNIST classifier, then loss function, then optimizer, and then it is passing these three output when you just if you call this particular function. And the pre-processing. So here basically what you are trying to do. Uh, uh, so here basically you are trying to extract the means like images of like MNIST, English MNIST, basically English alphabets are there. So those data sets basically you are going to extract, like train loader, test loader, and categories, all those things. And then this is for the train the model, right? So basically I am going to execute the model on the because in the GPU is there, right? If GPU is there, so you can check whether GPU is available or not. Okay, tosh.cuda is available. If this is the file, so if you have one GPU, the by default this GPU will be assigned. Okay, so that your execution time will like for executing your task, it will take the less time. So I am not sure whether there is any tools or not, whether it can convert or not. But with the help of now recent, all this, you know, AI tools such as Grok, ChatGPT, okay, DeepSeek, they can easily convert. If you just tell the PyTorch code, and then it can, convert it to the TensorFlow. But specific tools, I don't know. I don't have, it means I'm not at all aware about them. Okay, so then first what you will have to do, so you have to pass that model to the device. Okay, so when you are going to use the GPU environment, so everything, even model, data, everything you will have to pass or push onto the GPU. Okay, so device means this is basically device. So this is CUDA device. So the model to device. So now you are pushing this model into this particular CUDA environment or GPU. So now whatever the task, like your data or your model was running on the CPU, now you have pushed it into the GPU. Now you have pushed the model. Now once if you have pushed the model on the GPU, so now it is necessary that you have to push your data also in the GPU, then only it will be executed. Otherwise, let's say if you have just pushed the model and if you have not pushed your data onto the model, then it may not work. Okay, you may not be, you may get some error, or you may not be able to run, and still it will work in the CPU environment as well. So remember, you have to push the model, what model, along with the data. Okay, so now you see, so train, test, all the errors, losses you are computing. Then epochs, how many epochs you would like to run. Then training, train mode. Then batch losses, right? So then the data, train loader. So like you have extracted the images along with the labels. And then you have to push, because your model has already been pushed into the GPU. So then you have to push your image along with the labels to the GPU. Okay, so now you have pushed. Now your data is there. Now you perform the forward pass, the prediction, then back propagation, then some errors you are computing. Then this is the error, and this is basically the evolution mode. Okay, so now here also you can also see function. Now coming to the running the model, right? So this is your device. So this is your digit MNIST letter data set, and the digit data set, to number data, letter data, both you have loaded. Okay, then you have processed both the data set here, and then the visualizing the some categories of those data set, what kind of categories are there. Then train the letter model. So now created the model. Once you call the create the model will be created along with the loss function, and optimizer will be written, and then training the model. So when you are going to train the model, what happened was, what is there? Okay, create model is not defined. I think I might have not. Okay, I didn't call this function. Okay, so here, so now you have trained the model, right? So train and test accuracy you can plot here. Then evolution, coming to the evolution mode. Okay, so test letter model. So now basically now you are going to test evaluate on the number data set. So now you have loaded the number, then again you have passed through the into the GPU, and then you have predicted, and then you can see how much accuracy is basically coming right now. Okay, then fine tuning the model of the numbers. So now earlier we were fine tuning the entire model. right? But what you will have to do here, so you just want to fine tune the output layer, right? So as you can see, right? So this is basically the number model, means target, and this is basically your source model. Then from source to target, you are copying all the parameters. So now weight and biases are copied. But you know that in the last layer, right? So in the when you define the model, so here how many neurons were there, right? So in the last layer, if you see, there were 26, right? So okay, because there are 26 characters in the English alphabet. But when you are going to test it on the digit data set, so but there are how many characters, how many digits are there? 10 digits are there, right? So that's why this output layer again I have redefined. This fully connected layer again I have redefined. Okay, so here see the number model frozen dot, right? So this is your basically the model dot fc. So that particular layer you can extract, and then new definition you have given. Okay, so now after doing this new definition, so what I want, so accept means this particular layer fc2 layer, you are going to make required grade false. So what is the meaning of required grade false here? So me accept this newly added layer, all the layers gradient required gate will become the false, so that because of that they may not be trend. Okay, so that is the reason we have taken it here. Okay, so then only one layer you are going to outperform. Then after doing this thing, so now pass this particular model and you see the accuracy. So I hope it has already run. So see, if you have just trained the model, error rate you can see, so 1.23% only, this much error is coming. Okay, frozen the model and one epoch you have fine tuned it, train and test, so this much accuracy you are getting it here. Okay, so I hope if you have any problem, so just go through this code. Okay, if you face. So let me just complete one more pre-trained model like famous architectures. Okay, so just quickly I will go through it. As we are already running out of time, so just and 10 to 15 minutes I will complete. Okay. So different architectures you have seen. Okay, so different architectures you have seen. So these are the basically the different architectures, CNN models, LXNet, DenseNet, EfficientNet, GoogleNet. So, and when all these models were proposed, right? And how many layers are there and how many parameters are there. So if you compare here, so this MobileNet V1, okay, so it is containing more layers, and what it is having very few layer, 3.25 million parameters only. Okay, VGG19, if you compare among all the models, so this model is very bigger like VGG19, and it contains around 143.67 million parameters. Okay, so like that different architectures, so these models are available. Okay, so this is LeanNet. I think this is the Ayan LeCun, like he basically in 1998 he proposed this particular architecture. Then there is in 2012, so this LXNet architecture was proposed. Okay, so then it was trained by using this 1000 classes. Then VGG net was proposed. Okay, so then different layers are there. It is available in different like VGG19, VGG16. Then ResNet came, right? So here also the means as you can see, the output along with the output, previous output also is taken while computing the new gradient. Then here you can go through like different architectures are there. So if you click it here, so these many pre-trained models are there. So ResNet 50, ResNet 50. Okay, so all the definitions of different models are basically available here. Okay, so how they are trained, LXNet model, ConsNet, TenseNet. Okay, they are available with trained and without pre-trained also, like Vision Transformer, VJ Swing Transformer. Okay, so you can use and implement any of the architecture. Okay, for your problem. Okay, so now let just I am going to take a one ResNet architecture here. Okay, so this SLT data set basically we are going to implement. So here what we are going to do, so import the image data and download a pre-trained ResNet model and then fetch the model, replace the, because since this ResNet model is trained by using the 1000 classes, okay, then definitely the output layer, how many neurons will be there? 1000. Okay, but since you are going to fine tune on this SLT data set, okay, so in this SLT data set, basically this is also similar to the image cipher 10 data set, right? But it has most of the classes are unlabeled classes. So the properties of this are given over here. Okay, so what you can do here? So from this, because there are total 10 classes, right? So then you need to modify, you have to extract, that pre-trained model. You have to import that data first, SLT, and then download the pre-trained model, then fetch the model and replace the final layer as you did in the previous architecture, and then fine tune only the output layer. Okay, so as usual, right? So you are importing these libraries, okay, and then here, hello, sir. मैंने उनको बता दिया था सर, क्या बोलते हैं, समझदार सर को, तो वो बोल रहे थे प्रशांत को शायद वो अरेंज करके देंगे ना सर, उनको बताना था, आप ही बोल रहे। हाँ हाँ पहुंचने के लिए, तो वो सेफ्टी के हिसाब से और कन्वीनियंस के हिसाब से मेरे ख्याल से ट्रेन ज्यादा बेटर होगी। या फिर कार से चले सर, 3 लोग हैं तो 5-6 घंटे में पहुंच जाएंगे। कन्वीनियंस की है, जो ट्रेन की जर्नी का जो कंफर्ट रहेगा। हाँ हाँ, अच्छा ठीक है, तो सर वो ट्रेन से ही चलते फिर। आप ट्रेन से निकलिए, हाँ हाँ, 10 बजे पहुंच जाएंगे। शाम को कोई 5 बजे वहां से रिटर्न है, तो उसी ट्रेन से शाम को वापस आ जाएंगे, तो रात को 10 बजे घर आ जाएंगे। ठीक 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 है सर, ठीक है, ठीक है। मैं, हाँ हाँ हाँ, ठीक है सर, ठीक है, मैं बोल देता हूँ सर। ठीक ठीक, जी सर। सर आदि आप कर लेंगे सर, एक्चुअली मेरा लेक्चर चल रहा है अभी, तो यदि आप कर ले। हाँ हाँ, ठीक 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 है सर, थैंक यू सर। Sorry to interrupt. Okay, so guys, so see how to basically you can import the different models. So I have shown to you, right? So different architectures are there, like AlexNet is there, ConsNext is there. So what you will do, so just here Tars Vision. So one library I told, right? So this Tars Vision basically contains all the pre-trained model, all whatever they are defined here. So all the pre-trained models are available. So what you just need to do, guys, here, so tossvision.models.resnet. So let's say if you would like to extract the Miss VGG model. So just you have to write the tossvision.model.vgg 16. Okay, then pre-trend is equal to pre-trend. So if this is the false, okay, so just the architectures will come. Remember, guys, one more important, very important point here. Okay, so the architecture will come with the random weight. Okay, if you just write here pre-trend is equal to true. Okay, if the pre-trend is equal to true, then the the ResNet architecture, which was trained on the ImageNet with 1000 classes. So then whatever the weight and biases were there, so those things will come here. Okay, so that is very important point here. So then what basically I'm going to do here. Okay, after importing that architectures, you can also see, and then param in self parameter. So require grade, I am just going to make all the layers parameters as a false. Okay, so then I am freezing all the layers of this ResNet model. I am freezing. Okay, then just final classification layer. Then I am modifying. Earlier it was around like 512 comma 1000, right? So now what I am going to do, so I am going to replace it with the new layer. Okay, because you have only 10 classes, so that's why. So only the final classification layer I am going to modify. So nn dot layer linear 500 comma 10. Okay, then again I am pushing the model to the device. Then I am going to define the cross entropy loss function, then gradient descent, right? So I'm passing the parameters to it with learning rate. Okay, so all those things we are doing it here. So I'm running it here. Okay, so then again pre-processing the data and then visualizing those data, right? Definition, then the model I am training. Okay, so now so here you just check, like first the model is being first the data set is being downloaded. So it is a 2.64 GB data, so it will take little time, okay, to download it, that particular data. So here, so the model also, like you would like to see the architecture of the model, so you can pass this one architecture image size, and then the full architecture will be summarized. Then you can train the model, right? This is the classifier model you have trained, SLT10. Okay, so this is your class basically. So class is going to return all those things. Okay, so then you are pushing the classifier and then summarizing. Then you are plotting the result and then you are predicting. Okay, so same way, what you can do, guys, just go through the code. So try to replace, use the different pre-trained architectures, such as VGG16, VIT, okay, Google Net. Okay, so here you take and you see the accuracies, how basically the different architectures with this data set, how the behavior is like different, and how like different accuracies you are getting. Okay, so now I will stop myself here. So if you have any specific questions, so please ask me. Then I will upload this PPT. So if you have any questions or any doubts, so feel free to ask. Sir, can we can use a different optimizer loss functions, or we need to keep same? No, you can use different optimizer and different loss functions. I already told you, right? So like if it is a categorical data, so then you have to use the this cross entropy loss function. Or if your data is uh, like continuous data, so then you have to use the mean square error loss function. So both are available in that library, torch library, everything is available. Okay, so optimizer also you may use different, like right now I have been using the stochastic gradient descent, so you may use the Adam optimizer. So like there are different optimizers are there, so those things you can implement. So see, so pre-trained model, I'm not at all aware, like what are the, and is there any specific pre-trained models are available for videos or not? Yeah, but nowadays, like these pre-trained large language models, so similar kind of like whatever I have shown to you, like vision transform vision transform dot model dot ResNet you are writing. So then there are some specific large language models are there. Okay, so that large language models basically you can also customize this ChatGPT or this DeepSeek. Okay, so with your own data set also, that parameter already, that model already pre-trained. So like if we talk about the ChatGPT, if we talk about Grok, so they are also some pre-trained from, means they are already trained from some particular data set. But if you would like to implement it for your specific task, so those weight and biases of those pre-trained models you can take and you can customize it for your data set as well. If we use pre-trained model but output source overfitting, what should be done to improve the model performance? Yeah, overfitting, if you, it means pre-trained model transform we need to apply before the doing the train split. Or transform means like, let's say some architecture like transformer vision transformer models require some specific size input images. Okay, so when you are going to download, okay, so at that time you can while downloading itself you can normalize the data or you can resize the data. Okay, but it is not necessary that at the same time you have to do. So later also before giving the data to the training, right? So you have to do it before the training only. So either at the time of downloading or after downloading you can perform this transform. Is there any specific question? If we use pre-trained model but the output source overfitting. Okay, so overfitting means so what you can do, what should be done to improve the model performance. So if it is showing, so maybe you can add more and more layer as well. Okay, so right now in the model, what I did only just I replaced the output layer. But you can make the model more complicated, more complex as well. You can add like 2, 3 more layers or more layers you can add. Okay, so then I think your problem of overfitting will be solved. Okay, transformer form we need to apply before. Sir, details of the pre-trained models we can get from the PyTorch documenters, like how many layers. Yes, yes, yes. Okay, and definitely I told, right, in the code itself. 1 minute. One thing also you can do, what you can do. See, this is the detail architecture of the convolution layer here. Can you see it here? How many layers are there when you are passing that particular size images? So after each layer, what is the size of the output shape, and then how many parameters are there? Okay, so what you can do, so you take the, see what you can do, the take the model. So this is your classified.model is there. So ResNet model basically it is. Okay, and then comma, then pass one particular image, and then toss summary you pass to this function. So then entire detail, like how many layers, how many parameters in each and every layer. So it give you the detail. So how after like convolution, there is a batch normalization, then ReLU, then max pooling, then again convolution. So entire details you may get it. Here also you can get it. So then total number of parameters are like 11 lakh something, right? Trainable parameters are like these many, because some of them you have frozen, right? Most of the parameters you have frozen. Only output layer, you have not frozen, right? So that's why you can see it here. So these many parameters, like parameters only you can train the model. Okay, and non-parameter, because all rest of the parameters you have frozen. Okay, so what is the input size, back propagation time? So everything will be, means pass size, everything details will be given to you. So any other specific question? I think no more questions. So thank you very much, participants. Yes, sir. Sir, we can take only the architecture of the pre-trained model and do require the great false if we don't need its weight and bias. Yeah, you can take no, but the weight and bias is already there. Okay, but the means you cannot fine tune it. If you make this required grade false, so you cannot fine tune, but the parameters will be the will be the fine tune parameter only. Okay, but if you just want the architecture, I told, right? If you just want the architecture, so just you have to, this pre-trend is equal to, you have to make it as a false. If you just make it as a false, then random weight will come, not fine tune. Okay, so maybe in research related, like different architectures and how like we can improve the performance. So maybe in the Capsilon project, I will explain to you all those things. Thank you very much, guys. I think we can stop now. Yeah, I will share. Okay, this PPT I will immediately share with you so that you can access it. Thank you, guys. I hope you are attending all the lectures, and all the lectures we have decided in such means sir need more time to do the daily assignment. Yeah, you can request it to the coordinators. Yeah, you can request to the coordinators. Okay.